Thank you all for coming. I'm David Pollak. Nice name to have here in Krakow, at least the last part of it. I'm going to be talking about building and securing platform as a service using two technologies. One is called Docker, which many of you are probably familiar with. The other one is called Weave. So a little bit about me. I founded the Lift Web Framework project, wrote beginning Scala, and have been doing Scala development for almost 9 years now. I've written a bunch of commercial spreadsheets, but that was back in the 90s. I am the former vice president of engineering and CTO at a company called Nginx, which does web app security. So I've had a bunch of years in the trenches doing security work. I'm a lawyer by training, but use many different technologies. And so I'm wearing this T-shirt that one of the vendors is giving away in the foyer. And this is kind of me back in the day. I wrote a Commodore 64 program, actually put me through college, doing diagnostics on Commodore 64s and wearing, a classically trained Commodore 64 T-shirt I thought was fun and amusing. Okay, I guess nobody else does. So let's go on. Structure of the talk. I'm going to talk about the mechanics of securing a platform as a service using these two technologies. Then I'm going to talk, we're going to go through a demo. I'm going to talk about the philosophy, and if anybody wants to have a discussion, great. Although, given how dark it is and the light is shining in my eyes, I think it's going to be moderately problematic for me to see anybody with a raised hand. So let's get into the mechanics part. So kind of as a step back, one of the projects that I've been working on is analytics as a service. So allowing a user, a company, to upload some analytics to a cloud computing platform and run those analytics against data services, data streams, maybe some historical data. And basically making sure that each of the clusters of the user's analytics systems don't interfere with the other clusters of the user's analytics systems. Traditionally, that may have been done by having separate virtual machines, separate Amazon instances, whatever, for running the user's computations. The challenge with having separate analytics instances is that starting up an AWS instance takes time, whereas starting up something where you want to do something quickly on demand, being able to fire up what looks like an entire environment for a user within seconds is a lot more valuable than having to wait seconds, minutes, or multiple minutes to fire up a cluster and configure the cluster. So as we kind of go through the discussion of the analytics platform and how to secure individual clusters within the platform, I want to talk about 3 different threat models that I've been keeping in the back of my head. And when you do security, one of the ways of doing security is kind of looking at who's going to attack you, why, and how. And so here are the kind of 3 stories that I came up with that help guide me in the development of the system. First of all, if you've got an analytics platform and you're running some analysis, if somebody wants to attack your system, your cluster, they may want to discover data that you have. Maybe that's raw data, or maybe that is analyzed data. So, if you think about a drug manufacturer, they have a lot of information about clinical trials. If one of their competitors wants to access information about those clinical trials, being able to break into a system that happens to be resident in the cloud might be an interesting way of doing it. You also may want to discover a competitor's analytics. So it's not necessarily the data that you're interested in, but how they go about approaching analysis of the data. So, how does one airline analyze patterns of bookings, et cetera, so that they can figure out how to open up new routes, what have you. Being able to discover how your competitors are looking at data is also something valuable. And the third thing is being able to do a denial of service attack on a competitor system can be of value. So especially in real time, if you're doing financial work, if you can slow one of your competitors down, if you can basically cause stress on their system, you have an advantage because sometimes milliseconds count. So those are the three threat stories that I've been keeping in my head as I've been trying to figure out how to secure a system. So let's look at the technologies involved. The first one is Docker. Docker is the new hot stuff on the block, and it's new and hot, but it's really not much of anything other than a very, very nice user interface for programmers on top of a Linux facility called LXC containers. So basically it's a way of defining the contents of an LXC container, being able to execute stuff within an LXC container, and being able to capture information out of that execution. So an LXC container, if you're familiar with BSD, it's similar to BSD jails. There's a Solaris equivalent as well. It's basically a way of isolating not just disk access, but also access to other resources on the system. And the way that LXC containers are presented within Docker, it looks like you have a whole machine to yourself with explicit resources in the machine, even though that machine is actually just a process in a Linux box. The other thing that's nice about LXC containers and about Docker itself is that you can have different versions of libraries as long as the kernel supports those versions of the libraries across different Docker containers. So it eliminates a lot of the configuration problems that one has with more traditional Ansible or Puppet or Chef kind of ways of saying, here, make this machine the same as it was in another place. Docker is really nice because the cost of starting up a Docker process or Docker container is roughly the same as the cost of starting up a process in Linux. Maybe it's a little bit heavier weight, but not that much heavier weight. So within seconds, you can have a Docker container running that compares with minutes or longer for booting up an instance on a virtual machine. And also, the Docker definitions are very simple. Let me actually flip over to Emacs and show you one. So this is a Docker definition. The first line of the definition is, let's see, yeah, here's my red arrow. Just a comment. We say that we're deriving our image, the definition of what will run in a container, from Ubuntu 14.04. So basically, it looks like Ubuntu 14.04. We run apt-get, which basically downloads the latest version of the available libraries. We install wget, curl, telnet, and nmap, and then we add some of our own local files. So this defines an instance in Docker. This defines what we want our container to run, and the container only contains those things and nothing more. The nice thing about Docker files is they build the same machine wherever you go, but you can also ship around what are called Docker images, which are collections of layers of stuff built into a virtual file system. So the first layer here, each line here is a separate layer. So the first layer is the Ubuntu layer, which is pulled from a public repository. The second layer is what the file system looks like after apt-get update. The third layer is what happens after we run this command. Fourth layer is adding file, fifth layer, sixth layer, seventh layer. The nice thing is that if you've built some of these layers in the, on a local instance, you don't have to rebuild them. So if we have 5 or 6 different Docker definitions that all do a run apt-get on Ubuntu 14.04, you don't have to run this each time you build a new image. You can also ship the images around as blobs from one point to another. Oops. Come back here, presentation. Thank you. So this is a visual image of the difference between Docker and the traditional virtualization that we're familiar with. Another side benefit of Docker is that if you're sharing libraries, if you have a .so that are running across, that's running across a series of different containers, that .so is shared within kernel space or within however the kernel kind of loads shared libraries. So it reduces memory pressure, makes things marginally more efficient than running a whole OS inside a virtualization system. What you may be less familiar with is a technology called Weave. Weave is a virtual networking layer that interacts with Docker containers. So it's a way of creating a network across hosts, across multiple machines running Docker containers that appears to be one network or one subnet or multiple subnets. And each of the containers that is attached to the Weave network sees a virtual container. So when you combine, and actually let me show you a picture of it. So what we have here is we have a series of Weave instances running on a series of different hosts, different physical machines, but they present one virtual network that has the same kind of rules that apply to the virtual network that apply to any other networking that we're familiar with. And the nice thing about that is we can use the same networking tools, we can use the same networking understanding that sysadmins have on the virtual network, the same way that we would isolate or apply that knowledge to a physical network. So how do I think about, or how did I go about securing the platform as service that I built? So kind of as a big picture, each of the tenants, each of the separate users will have its own Spark cluster. That Spark cluster has to talk to the real world. And that Spark cluster also has to talk to a bunch of back-end services. But the thing that the Spark clusters can't do is talk to each other because each of the Spark clusters is owned by a separate tenant. Within each cluster, we have one or more nodes that can talk to each other, they can see each other. They can talk to the real world, and they can talk to back-end services. But once again, they can't talk to each other. So when we kind of start building our threat model, we look at the different ways that code running inside a cluster can perform some behaviors that we don't want. And the first one is that an application can talk to the host, can talk to the machine running the container via code. And that threat model is pretty well taken care of by Docker. Docker does good isolation, or more specifically, the Linux kernel does good isolation of LXC processes. What's more important here is that people who know security are looking at the issue, and because Docker and LXC containers are becoming an increasingly important part of the overall Linux ecosystem, lots of people are working hard to make sure that the isolation that is stated is actually the isolation that's delivered. The next threat model is application to host via network. So can the application see the host that it's running on through the network interface rather than through physical code calling into some kernel routine or something? The third threat model is application to application across the network. So this is the threat model where cluster 1 can't see cluster 2. And finally, there's a threat model of some malicious code within a container talking to a back-end service and accessing data that they shouldn't access in the back-end service. So as I said, the Docker instances are reasonably well isolated from the host, and there is ongoing work to make sure that the guarantees are there. The Weave subnets do a very good job of isolating the different networks from each other, so that the applications on subnet 1 can't access the packets on the applications on subnet 2. And when we talk to the back-end services, we only talk through HTTP, through a SQUID proxy, using credentials, so that we know where the traffic is coming from, we know who is presenting the traffic, and using SQUID, which is a proxy, an HTTP proxy, we can add additional isolation rules if necessary. So the clusters can see nodes within the cluster, they can see the world, they can see services. They cannot see other clusters, they can't see Docker hosts. So, and the other thing is that clusters may span multiple hosts. So you may have 4 or 5 or 6 clusters, or you may have 4 or 5 or 6 nodes in a given cluster spanning a bunch of different hosts. You can also have multiple different clusters running on the same host. So we use Docker to constrain what the contents of the container can do. We start by disallowing networking. So when we fire up a Docker container, we don't give it any networking privileges at all. By default, Docker containers, when they're started, are given access to network with other Docker containers on the same host. By default, they're given access to basically the host's NIC to send packets out beyond the host. We disallow this with a Docker option called net equals none. There's also a potential attack that an app running in a container can perform, a denial of service attack, and that's by using up all the available memory on the host. And we take care of this attack by basically saying that a particular node, a particular Docker container can use no more than 300 megabytes of memory. This is going to change app by app. And also that the total memory plus swap space is also 300 megabytes. So an individual container can't cause the host to swap, which means that the individual container can't cause the host to go and perform more I/O ops than the container that will basically deny some services or all services to other nodes running on, or other containers running on the same host. By default, the Docker defaults for CPU allocation are just fine. Basically, it's the same as a Linux allocation, although you can do things to throttle CPU utilization down on a container-by-container basis. Each Docker container appears to be its own machine with its own file system. Docker only allows 10 gigabytes of data to be written by default to the local file system, and after that, it will just run out of disk, or the container will run out of disk. So I should also step back and say it's possible to mount particular volumes into a container from the host. So if you want to allocate space for writing large tables, if you want to allocate space for a Hadoop file system, what have you, you can do it on the volumes on the host by just mounting those to each of the containers. But the core file system for the container itself is limited to 10 gigabytes. So, a container decides to try to use up all the disk on a host. It can't do it because it's limited to 10 gig. So the untrusted code in the containers can only communicate via HTTP or HTTPS through a SQUID proxy. The SQUID proxy is trusted to route HTTP traffic the right way. And once again, SQUID can be tuned to disallow access to certain resources, disallow access to certain IP addresses, etc. In terms of networking, in my instance, I allocate a /24 network, 253 network addresses per cluster. And using the weave attach command, we basically attach a 10.whatever to our node. And we put all the nodes on the same subnet. We add SQUID to the subnet so that each of the nodes knows where to do its HTTP proxying. And because Weave spans hosts, even if the nodes are running on separate hosts, as long as they're part of the same network, which they are, the same /24 network, they can see each other. So let's go and do this as a demo. Can all of you see, is the text big enough on the screen? Awesome. So I just did a Docker PS to show me all of my running Docker containers. And you can see we've got SQUID and we have something called serve. What serve is it's a proxy for a backend service. And let's see, in this window, we're actually going to log the HTTP requests made to serve from our various different subnets. So the first thing I'm going to do is I'm going to fire up a worker on 10.4.1.2. So we're going to fire up our worker. We're attaching the squid proxy to the network, and momentarily we should be able to see, whoops. You can see that the particular worker here is something simple. It's going out and pulling off the list of, pulling down the home page from one of the sites in the list of the 1,000 most popular sites. So it's going out and doing an HTTP request through the squid proxy, pulling down the site, and logging the request back to our faux backend service. So if you can see here, I can't even see it, but this is a site that we just pulled down. You know what, let me make this bigger. So this is a site that we just pulled down, and this is the unique identifier for our backend service. So let me go and fire up a second backend service, and it's going to be on 10.4.2.2. So it's on a separate subnet. Once again, we're attaching squid. And we can see that we have traffic that's coming from the second subnet, and we should see something coming from the first subnet. The guy in the first subnet is doing much better than the process in the process in the second subnet is doing much better than the process in the first subnet. Okay. Well, anyway, we can see that stuff is happening. And now what I'm going to do is I'm going to attach a port scanner to the first network. And there's a tool called Nmap, Network Mapper. And what Network Mapper does is it scans all of the IP addresses in a given range of hosts. It tells you all of the hosts that it can see. Then it goes and tries to do TCP/IP connection, make a TCP/IP connection to 1,000 of the most popular application ports on each of the hosts that it finds. So what we're going to do is we're going to scan both of the subnets to try to figure out whether or not we can see from our first subnet the second subnet. So let's just do an ifconfig. And we can see as we're on virtual subnet 10.4.1, and we're going to run our scanner. Forgot what the name of the scanner is. Port scan. So we have a whole bunch of messages saying that we're unable to determine the route to 10.4.0, 10.4.2, or 10.4.3. So we're actually seeing an isolation of the networks already. And when I was rehearsing the talk, it takes about 2 minutes to run the port scan across all of the networks. But the net is that we're seeing early indications that we're not able to see from subnet number 1, from cluster number 1, into the machines in cluster number 2. So I will go back to the presentation, and we will come back 2 minutes later and see how things went. So I've shown how the mechanics of creating the separation of networks using Docker, using Weave, and using Squid. I've shown that we can basically have 2 isolated subnets talking through Squid to a back-end service and also talking to the outside world. But let me go through and do a little bit of philosophy because, you know, as a developer, I'm an arm-waving philosopher about much in the world of computing. So let's kind of take a step back and look at some recent and notable security failures. Freak, Heartbleed. You know, basically, you can make an HTTP, or you can do some nastiness with SSL to be able to read the contents of memory on any machine that you're connecting to via SSL. Shell shock. Bash has been around for, what, 15, 20 years now, and there was a problem in a regular expression that was supposed to clean some data, and because of this, it was possible to send malicious data into a web server and cause the execution of code on a remote system. A big department store in the US called Target lost, 15, 20 million credit cards last year. They lost them because of an SQL injection attack. All of these attacks were failures to interpret data. So there's data on the wire that comes in. In each of these cases, because of a programmer error, the programmer failed to interpret the data correctly on the wire, and that led to either exposing the systems to having remote code executed on the systems, or exposing data within the systems. Actually, let me pop back. I think our 2 minutes are up. Yes. So we've finished our port scan, and we can see that our port scanner only found that there's a host at 10.4.1.2, the host that's running our app. There's a host at 10.4.1.240, our Squid proxy, and it turns out that it has one TCP/IP port open. And then the host that's running our port scanner. So using a tool that maps networks, we've demonstrated that there's no cross-network traffic. Anyway, back to the regular presentation. So in each of these cases, we failed to interpret data. OWASP is an organization that basically promotes web security. And they have a top 10 set of vulnerabilities for software running on the internet. The first one is injections. An application sends untrusted data to an interpreter. The interpreter misinterprets the data and does something bad. The second one is cross-site scripting, where an application includes data that's sent back down to a web page in a way that's not properly encoded, and basically allows for the insertion of a script that runs in the client. Once you've inserted a script that runs in the client, then the script has the ability to do anything that the client can do, including reading local data, making requests, HTTP requests on behalf of the owner with the owner's credentials, and possibly taking that data and then sending it back to a third-party server. And also cross-site request forgery, which is a variation on cross-site scripting where you can basically, once again, take over and make a web browser do something in the name of a given user maliciously and take the data back. And all of this leads down to never trust what's on the wire. Whoops. And never push the wrong button in the middle of a presentation. So what if what's on the wire is Turing Complete? Once again, I was building platform as a service that runs an analytics service. So by definition, the analytics information, the program that is doing the analysis is Turing Complete. So how do we secure a system where we know the user is going to be uploading code that is Turing Complete? And, being a little bit less philosophical, Turing Complete means executable code. Now, there are a bunch of examples of things that are Turing Complete that we might not think of as Turing Complete. My son is 10, and he's currently very, very, very addicted to, hyper interested in a card game called Magic the Gathering. It turns out that the rules to Magic the Gathering and certain cards in Magic the Gathering lead to Turing Completeness. You can actually run loops and branches in Magic using standard rules and standard cards. MediaWiki templates are Turing Complete. You upload a MediaWiki template to something, the thing that's interpreting the MediaWiki template is actually interpreting something that's Turing Complete. The Apache rewrite rules for the 3 people that are still using the Apache web server rather than Nginx or HAProxy, the rewrite rules are Turing complete, and so if you allow somebody to upload rewrite rules into your Apache system, users might want to configure their own web servers or whatever, you're allowing them to upload Turing complete programs. And my favorite, Excel. Yes, Excel is in fact Turing complete without macros. So if you allow users to upload an Excel spreadsheet and run the Excel spreadsheet, you're actually allowing them to run Turing complete code. So if it's Turing complete, it can do anything that any other program can do. And no matter what you think, it's really, really hard to secure something that's Turing complete. It's really, really hard to clean the program, to figure out, okay, is it doing something that we're not intending? Is it doing something that's malicious? And looking at shell shock, how did the folks who wrote Bash try to, clean the data or interpret the data as data versus executable shell script? They used a regular expression. It turns out that there was a mistake in the regular expression that led to having a couple of curly braces in a particular order caused the regular expression to say, oh, no, that's fine, even though it wasn't fine. So trying to clean a program by saying, we're going to pre-interpret its contents and clean out the stuff that we don't like is a traditionally very bad way of doing security. Finding the right place to secure a system, to secure an application, is key. So knowing where you're going to secure something, rather than saying, oh, we're smart, we'll write a regular expression that will pull the bad code out and leave the good code in, is not a good idea. Whereas if you use more traditional tools, how to isolate something and only allow it to perform certain actions, because you know that if you've got malicious code, the code is going to perform those actions. That, to me, philosophically, is a much better way of securing something. So let's talk about securing things. People come to me and say, Dave, you do security. How can I make sure that my data is perfectly secure? And the answer is add a lot of entropy. If you've got some important data on a hard drive and you never want it to be read by anybody ever, you take it and you throw it into a volcano. It's enough entropy to kind of like make whatever the thermodynamic definition of your data disappear into a much larger thermodynamic system. But short of that, it's really hard to actually secure the data. And the bigger question is, how do you secure data and make it accessible to others? And the answer to that is layers. We have layers in biology. We have this nice skin stuff that wraps our bodies that is particularly good at keeping the malicious agents out, letting the non-malicious things come in, like, oxygen, water, food. And our skin is actually a series of different layers. Our skin is pretty complex, nifty stuff. We have layers in clothing. I live in San Francisco. It can be 55 or 45 degrees in the morning. It can go up to 75 degrees in the middle of the day, and then the fog rolls in and it's 55 degrees again. My kids are always wrapped in layers. Wear a t-shirt, wear a shirt over your t-shirt, wear a jacket, maybe take a sweater with you. Okay, do I sound like my grandmother? Yes, I don't know where that came from. Layers in clothing also help protect us from not just weather, but from rain. Well, I guess rain's weather. Anyway, layers in castles. When you build a castle, and my son is doing this in Minecraft, he's like, okay, I want to build a secure area. Well, I'm going to build a moat. I'm like, okay, I'll jump over the moat. He's like, okay, I'm going to build walls. You kind of go through, and no single layer is impenetrable, but taken as a collection, you get two things. The first thing that you get with layers is you get the ability to slow your attacker down. Secondly, you get the ability to identify that somebody is attacking you. So it may very well be that somebody is particularly stealthy and you don't see them, but if you see a hole in the wall, you know somebody's attacking you. So using layers as part of a security and isolation mechanism is really important. We also see this as layers in physical security. You know, you have the important thing at the center and you build layers around the important thing. It's a variation on the medieval castle. So layers are a start. Mentality is also extraordinarily important, as is granularity. So when you're building a secure system, you don't want the knowledge of the secure system, the ability to manage the secure system, be resident in the head of one person. You want to be able to hire people to replace other people who do security-related things, which means two things. The first thing is that whatever was done has to be reproducible with scripts or programmatically. It means that the programs that do the actions have to be understandable. They're not write-only scripts. They're things that have to be understandable by multiple people. And there are things that have to be reliably executable. So each time you execute it, you get the same output. And a lot of what we've done in system administration over the last 20-ish years and probably before that are things that lead to reproducibility. So we all know how a network works, or sysadmins know how networks work. They know how network partitions work. They know how TCP/IP or how packets can traverse networks. Building something that is oriented towards things that people already know makes a lot of sense. The second thing is that if you're going to do a secure system, hiring people that have an untrusting mentality is important. And the untrusting mentality can be an untrusting mentality like testers. QA people have a particular kind of, I want to break this untrusting mentality. I know there's a bug in there. I don't trust that the code will work the way it's defined, so I'm going to figure out a way of breaking it. Security people think about attack vectors. They think about ways that somebody will come in and try to get access to the data. They'll think about threat models. Hiring people that have that mentality is an important way of securing your system. One of my pet peeves is the JVM security manager. I mean, I've been using Java for more than 20 years now. Yeah, that makes me old. I was born before the internet, but I already went through that in the first slide. The security manager tries to control access to resources at a way, way granular level. And if we compare that to the way that we've approached things with Docker and Weave and Squid, they're at a much coarser level, a much easier to understand level. So if you're going to try to use the Java Security Manager, which is, if you're running a Spark cluster, you might basically say, oh, okay, I'll just load the Spark instances up with a class loader that implements a bunch of the security stuff, and then people won't be able to talk across whatever. Getting stuff right in the Security Manager is really, really difficult. Getting stuff right by turning on and off network switches, by being able to say you can do whatever you want within this container because you can't break out of the container. Those are much easier ways of securing a system. Finally, when you think about security, when you have a mentality about security, you want to have the intended consequences. You want to have the default thing be right. So bringing up a container without networking and then explicitly adding networking to it is materially different than saying, I'm going to bring it up with networking, and then I'm going to do something with the packet filters or with IP tables or something to constrain what's going on. So building up secure pieces on top of things rather than trying to wrapper things around something that is not secure, I think is a better approach. Finally, when you're building a platform as a service, things are different than just normal security. So with normal security, it's to a certain degree, and this is becoming less true, especially after the Sony hack last year, but security is, in general, what some people call the egg model. It's got a hard shell on the outside and a soft center on the inside. But when you're building platform as a service, the stuff that's running inside your cluster is just as untrusted as the stuff coming in from the outside world. The users, when you're building platform as a service, you have to make sure that the users have access to the resources that they're supposed to have access to, but they don't have access to anything beyond those resources. You have to think multi-tenant rather than single-tenant, and trying to isolate each of those tenants in an appropriate way rather than say, we're going to build this hard shell around the outside of our program, our application, our system, and leave the inside soft. And it's actually interesting, there was a security breach at a company that does password storage. So, there are a bunch of companies out there that will let you have, will store your passwords for you in an encrypted format and let you access them from a variety of devices, and it's seamless to transmit your data across those devices. And it turns out that one of those companies was recently breached. I can't remember the name of it because I run my own server that transmits the passwords because I'm hellishly paranoid. But it turns out that these guys, they did have a smart model on the inside as well as the outside, but the one thing that they didn't do was they didn't have rotating credential updates. So the same credentials were used to access the database from all of the various different hosts that were accessing the database, rather than having a per host password that was then changed up frequently. So once the attackers got onto one of the hosts and got access to the key file for the passwords, then they were able to read the passwords out of the database and then exfiltrate them. So once again, it's something where they had a mostly hard on the outside and more trusting on the inside approach to security, rather than an approach to security that says every machine, even the machines that we own, are untrusted. The final thing with platform as a service is you want to be able to meter, log, and throttle usage. And one of the things that's nice about Docker is it allows you to do all three of those. So you can basically meter the CPU utilization on a per container basis. You can log resource utilization on a per container basis. And you can also throttle CPU utilization, memory utilization, and other resource utilization on a per container basis. So when you're building a shared service, you want to share with care. The shared services are in fact subject to attack. So the back-end logging service, what have you, are potentially going to be attack vectors from the untrusted code running in the per customer cluster. So even if even if the nodes can't see other tenants' nodes, if you can get into one of the back-end systems, then you have the potential of accessing the system, the broader system as a whole, or potentially accessing other customers' information. So in general, when I build services that are going to be shared by multiple untrusted parties, I try to make them either read-only or write-only. You may say, what's a write-only service? A log is a write-only service. Yes, granted, you do an HTTP request to post a log someplace and you get a 200 back saying, yeah, the log entry was posted, but you don't get any information beyond a 200, yeah, I got that. So when you write data, all you get is an acknowledgement. When you make a request to read data, all you get is the data that you're reading. You don't have the ability to do a read, modify, write on an external system. So you don't have the ability to run an update or an insert or something on a remote system. You're basically going to be dealing with REST services. You also have careful attachment to the shared services. So in the example that I ran, we have one shared squid proxy that's spanning all the services. What you might do if you're running a series of untrusted code is proxy through a per tenant squid instance and have that squid instance modify the HTTP headers that go to backend services, because you're going to trust the squid instance and trust it to modify the headers. So you might modify the headers to say this came from X, this has credentials Y, etc., and then do some checking on the back end. You might also run a separate squid proxy on the back end or a reverse proxy on the back end to make sure that all the requests are authenticated before they actually hit the services. Once again, layers. The most important thing, and this is the whole weave thing, is you forbid cross-LAN traffic. You just do not let LANs talk to each other, because there's no telling what you can do across a LAN. There's no telling how you can attack a service if you can send TCP/IP packets between different tenants. So we've taken a look at applying the philosophy, and we're using proven tools. We're using network isolation, which is something that system administrators know and trust. We're using Linux LXC containers with a nice Docker UI on top of them to be able to create our code execution isolation environments. We're using Squid to make sure that our HTTP traffic is correct. Each of these pieces is understandable by people that you can hire on the street. Well, maybe not on the street, but if you put out a job rec for somebody who understands Linux system administration, networking, and can configure Squid, here in Krakow, I bet you'll have 20 applicants tomorrow for a position with those qualifications. It doesn't require anything that is proprietary. It doesn't require anything that is learned beyond understanding specific scripts. And finally, all of these things can be managed with scripts. And whether the scripts are bash scripts, which is the example code that I have, or the scripts are Puppet or Chef or Ansible or something else, these are things that are well known, well understood, and once again, you can hire for them. There's no super cool magic of a security manager that your smart guy wrote in Go, and then the smart guy left and nobody can maintain the code. So to wrap up about 10 minutes early, we have, kind of mentality-wise, we've gone from isolating code by having code run on individual machines to isolating code through virtualization, and now we're isolating code using LXC containers and Docker. Network isolation is easy. We've been doing it for years. We've been securing networks with firewalls. That's all well-known, well-understood technology. And if you're building a platform as a service or any other thing where you're going to allow end users to upload code or anything else that's potentially Turing Complete, Docker containers and Squid and Weave are a layer in your security model. So that's it. I appreciate your time. Maybe we can bring up the lights if anybody has any questions. Yes, sir.
One question I've got around Docker, a lot of the power, the things that people like about Docker is the fact that I can use other people's images. What are your thoughts though about those trust models? I've got to rely not only on the person who's container I'm using Docker, but also who they depend on. I mean, do you use those third-party definitions, or do you roll your own?
So the question is, how trustworthy are the open source Docker containers? And the answer is twofold. The first fold is that there was recently a blog post that over 30% of Docker containers contain code with CVEs in them. So, basically, if you're relying on somebody else's Docker containers, there's potentially known vulnerabilities in them. One of the projects that I've been working on is actually security analysis of Docker containers that you deploy as a service to address that specific concern. More broadly, the Docker ecosystem is younger than the Maven ecosystem, then the NPM ecosystem, then, you know, whatever, name your package manager ecosystem. The ability to insert malicious code into open source and openly hosted things, whether those are JVM things or JavaScript things or whatever the other things are, exists, and it has existed. What we're seeing in a lot of the other communities, for example, the Nexus people just, what was it, about a year ago, they went to SSL only for downloading anything from Maven Central. Before that, it was like, hey, you know, HTTP, HTTPS, it's all the same to us. So we're starting to see that more of a security mentality. The Docker people are among the sharper people that I've met, and they actually take security seriously and are doing a lot of security things right from day one. You know, will there be an incident? Yes. Are they doing a lot of the right things from early on? Yes. All the Docker stuff is HTTPS. I mean, even their documentation cites HTTPS. All of the public images have full Docker files listed as part of the image. The way that the images are built, they're built layered, and you can actually analyze each of the separate layers to figure out whether the layers contain anything malicious. Me personally, I build off of well-known containers. So I'll build off the Ubuntu containers that are actually signed. I'll build off of the Java containers that are actually signed. I'm doing a project with that uses Python, and there are some signed Python containers, you know, that have Python and Flask and a few other things. But, you know, am I going to use Joe Bob's what have you container? Not for anything I care about. Sorry for the long-winded. Do we have other questions? Nope. Well, thank you all for coming. I hope you have a great DevOps, and, you know, thanks for having me.